Swayam Prabha. Digital India. Educated India.
This part of the course will begin with the nonlinear control design. So, we'll have some small chunks in which I'll post this, so that you can look at this a little bit of a thing in and ponder over. Okay, you don't want to kind of continue in one chunk everything. So we'll begin with some preliminaries of design for nonlinear control systems. So let me get to the slides. Okay, now in this we will basically look at Lyapunov theory. Okay, one of very important tools in the nonlinear control analysis. So you see that this Lyapunov theory is an analysis tool. Okay, it's not a synthesis tool. So you need to propose a control and check out whether it will be working. So this will be the some kind of a iterative design. You propose a control and find some kind of a stability proof for that. If you don't get, propose another control like that till the time you kind of get some stability proof. Okay, and this Lyapunov theory has been extensively used in many different kind of new control techniques design. So it forms some kind of a fundamental foundation for nonlinear control. Okay, and here we are looking at mainly application perspective. So we will present some kind of a preliminary mathematics which is at most essential for development of some of these control strategies, but mainly our focus is going to be on application rather than the proofs of the theorem for the for what Lyapunov has proposed. So I'll present you some of these theorems, but will not get into the details of the proof of them, because our main focus is going to be on application. Okay. So this theory, as we see it. So first we get into some fundamental mathematical preliminaries and define various notions of stability, as I mentioned earlier also, that from linear systems to nonlinear systems there are different notions of stability that one needs to get into. Okay, so let me just check things are getting recorded properly and then come back. Just a moment. Yeah, I think this we are fine. So let's see, start with these preliminaries now. Okay, so first is a notion of stability. So this Lyapunov, if you consider this, all these Lyapunov's theorems and stability notions, etc., are developed based on the this state form of nonlinear equation. So x dot is equal to f of t comma x. Okay, where x is a vector and u, if it is function, it is a function of x or it is a function of time. Whatever way it is incorporated in this function f here. Now the equilibrium of such a system is obtained by setting x dot is equal to 0. The very first important concept. At equilibrium, you want to know what is the equilibrium of a system. You set x dot is equal to 0, whatever you get will be equilibrium of a system. Okay, and we assume that this equilibrium, when you set x dot is equal to 0, in this kind of a form is 0. Okay, so if it is not 0, what you do is basically shift the new x. You say new x1 is equal to some x minus that equilibrium state, and in that, when you now see your equilibrium of a system, that will be zero. Okay, so it's important to make sure that all the equilibrium that we are talking about in this when you do this analysis is considered to be zero. So now we assume that okay, this whatever system way it has been defined has equilibrium zero. Okay, that means when we put x dot is equal to 0, we get x to be equal to 0. Okay, so that equilibrium 0 in the Lyapunov's notion, first notion of stability, is a stable kind of a system, is said to be stable if for each epsilon greater than 0 and each t belonging to this positive real line, there exists a delta which is function of epsilon and t such that this condition is satisfied. This S is a solution trajectory of this equation near equilibrium. Okay, so what it means is if I have the initial state, okay, developing uh, in this ball of radius delta. Okay, so what you have here is this norm of x0. Okay, so this x0 is the initial condition. Okay, so we start off with x0 as the initial condition at time t0. Okay, and we see the evolution of this trajectory. Now this evolution of the trajectory is less than epsilon for all t greater than t0. Okay, then we say that the system has a stability notion, this stability notion. So but it says that if for each epsilon you are able to find delta. Okay, so you are first given this epsilon bound on the trajectory, okay, as it evolves in time. Okay, so once you have given this bound on the trajectory norm, okay, so this is when you say this like a second norm, or like you can consider this as a square root of all squares of the term of this vector. Okay, these both the norms. Okay, norm 2 kind of you can use whatever norm you want to use, but typically norm 2 is used. Now, so you start off with this epsilon radius. So this is an example on the in some kind of a planar or a two-state kind of a system. So x consists of a two-state, x1 and x2 kind of a states. So you have this ball of radius epsilon around the equilibrium. Okay, so this epsilon ball is where your solution trajectories should restrict. Then you are able to find some delta which is greater than 0. Okay, so the delta should not be 0. So if you are starting at 0 state, then you know that by the definition of equilibrium you will remain at the equilibrium only. But you need to have little bit kind of a away from 0, so this delta is greater than 0, such that for x0 beginning into the, so delta is some smaller kind of a region. So suppose my x0 evolves in this starts off in this delta region, then my solution trajectories all are constrained to this ball of radius epsilon. Okay, if you are able to find such data, this is like a base fundamental definition of stability for the Lyapunov's sense. Okay, so for a nonlinear system, this kind of a base stability definition is used, and then you derive many other kind of conditions based on this fundamental definition of stability. Okay, then we have other kind of definitions coming up here. So for the same system, this equilibrium same now 0 is our equilibrium is attractive if for each time greater than time belonging to r plus real line there is eta which is greater than 0, such that this solution trajectory tends to 0, okay, as t tends to infinity. Okay, so what it means is like the solution trajectories not only remain now in the ball of epsilon, but they actually tend to go to 0 as t tends to infinity. Then the equilibrium is attractive. Okay, so x0 constraint in some kind of a ball of radius eta. Okay, so you begin with this eta is greater than 0. So again, you are not supposed to be on the at the equilibrium point. You can go a little bit. So your initial state should be away from equilibrium point by some small amount, and if under that situation, your solution trajectories actually go to 0 eventually as t tends to infinity, then your equilibrium is attractive. So that is a definition. So here, like, you can construct some kind of a ball of radius eta, and you start off those solution trajectories. They don't come out of this eta, but they actually go to 0. Okay, so these solution trajectories are actually attracted to the equilibrium, and then the system becomes attractive. Okay. So it is, see, look here, it is said that the solution trajectories, okay, not necessarily remain in the ball of radius eta. Okay, so they may go out of that ball, but they may come back eventually and go to 0. That is what is this definition says. Okay, and for asymptotic stability, okay, this is we have to define some notions. Okay, no, there are these different notions are for the next thing, but for asymptotic stability, it needs to be stable and attractive. Okay, so this is another notion of stability where it is not only stable but it is attractive also. The equilibrium is attractive also, and equilibrium is stable in this sense. Okay, so stable and attractive, both our properties are there, then, like, you have a asymptotic stability. Okay, so these are the basic fundamental notions here. So we'll introduce some more notions for the definition and for some analysis purposes, so that we will be able to apply Lyapunov theory. Okay, so this some of you may be familiar with the function. Okay, this function is defined on the time and vector Rn. Okay, taking into R. So this particular kind of a function is coming up in the Lyapunov theory later as a Lyapunov candidate, they call it. Okay, for stability purposes. Okay, so this is defined over time and this vector Rn. So same as, like, what we have in this definition of f, time and x. Okay, so it's a function of, like, general function of time and vector Rn, and it's said to be locally positive definite function. Okay, namely like LPDF. If it is continuous, then it needs to have the property that v of t comma 0 is equal to 0. So whenever this vector state is 0, you get the value of the function to be 0. For all t greater than 0, this should be valid. Okay, so this is another property, and then there exists a constant r greater than 0, and a function alpha of class k. Now we'll see what is a class k function, such that this function is bounded by from below. It is like the lower bound for this function, bounded from below by this function of class k. So this class k function we'll see first, and then, like, we'll come back to this definition. Okay, so this class k function is a function which is monotonically increasing function. Okay, so it is continuous, strictly increasing. This class k function, if you see this, it is strictly increasing, sorry, I'll get a pointer right here. So this is strictly increasing function here, okay, continuous function, and positive for x other than 0. Okay, so it is a 0 for x is equal to 0, same as like v function, and this has no time dependency. Class K function is only function of state. Okay, there is no time dependency of class K function. Okay, so if you see this alpha is only of x, okay, there is no time coming here. Okay, so for such a this alpha is a function by which this v is bounded from the lower side. So v is always greater than alpha of class K. Then this function is called locally positive definite function. This is like, again, most fundamental definition of these the Lyapunov function candidates. Okay, LPDF function. For function to be LPDF, you have to have these conditions. So that means this function v of t comma x cannot touch the x-axis here. Okay, it cannot come to 0 again. Okay, once it is 0 only at x is equal to 0, and now you see for any other value it cannot come to 0 again within the ball of radius r. Okay, so this is important. So this is for local definition. You need to have this ball of radius r at least for some kind of a norm of limit on the norm of x. It is valid, it's okay, then that is a locally positive definite function. Okay, so this is a base definition for the locally positive definite function, and if this r is extended now to the entire space, r tends to infinity, then this will become a positive definite function. We don't say globally, but it is positive definite function. Okay, so that is a main kind of a definition here. Okay, so again the same thing, the positive definite function, the function is said to be PDF if it is continuous, same condition as before. Then it has v is equal to 0 for all t when x is 0, this Rn vector which we are having it function of. And then there exists a function of alpha of class K such that now this function is bounded from below by this function alpha of class K for all Rn space. Okay, and for all t greater than 0, of course, which was there already for the LPDF case. Okay, so if you just plot, I mean, I'm just kind of this showing these plots, some kind of a schematics to kind of make sure the understanding happens really well. It's actually Rn space, and we may be able to see this function like this only if it is a function of x alone. If it has some kind of a time axis, we are not putting the time axis on this plot. So you may see that, okay, the function may have some kind of a time variation also at the same x norm possibility is there, but we are not kind of capturing that part in here. Okay, so this is just to kind of see some kind of a graphical illustration of what it means. Okay. So now let us see some examples. Okay, so we need to check whether these conditions are valid for these functions or not. Okay, so you remember the definition, you need to have a function of class K, and v should be continuous. So these are the conditions: continuous, and v of 0 is 0, and function condition on these for non-zero x. Okay, class K function condition. Okay, so we need to strictly follow these properties for checking whether these functions are positive definite or not. So if you see this function, for example, what do you think? Just do a little bit of a thinking whether this is continuous. Yes, it is continuous. Whether v if I put x is equal to 0 state here, I get v is equal to 0 for any time. Yes, that is valid here. Now it is bounded from below by class K function. Can you see that? So you find some function by which it is bounded from below, and I think this is done. Okay, so this is satisfying all the conditions, and that's why it is a positive definite function. Now if I see this function, okay, this is a function of x1, x2, x3, and this state is also given as x1, x2, x3. Okay, so when you have first thing you need to check whether all the state components are showing up in the function or not. So if you see these conditions, is it continuous? Yes, it is continuous. Then this, suppose I put x1, x2, x3 0, x is equal to 0 in the v, then v is indeed is equal to 0, and now this class K function condition is satisfying that, okay, for all other values of v, okay, other than 0 x, okay, this function is not taking value 0 anytime. So this is also a positive definite function. But now if I define this function x1 raised to 4, x2 raised to 2, okay, and I have this as a state, okay, then we need to see whether this is positive definite function. Okay, so see, although the form looks similar to this function, first condition gets satisfied, second condition gets satisfied, but the third condition, you see there is some problem. Okay, see, this x3 component is not showing up here. So for even if x3 is positive, okay, then the norm x is not equal to 0. Norm x is some kind of a finite value here. But if x1 and x2 are 0, then this function is taking value 0. Okay, this is not allowed. So that's why this is not a positive definite function. If the state is x1, x2, x3, if the state is given to be x1 and x2 alone, then this becomes a positive definite function. So that is a catch here that we need to be careful about. Okay, when x1 is defined as the state for this function, then it is not positive definite function. But if x1 is defined as a state consisting of x1 and x2 alone, then this is a positive definite function. Clear? This is what is the main crux we need to look for in the examples. Okay. Typically we tend to miss, because like, okay, we know, okay, these are all kind of terms which are positive, and then we don't see really, okay, what state we are looking for. Okay, so that's a kind of important condition. So these other definitions are again based on, if you understand class K functions, then this is putting some more conditions on these. These are the conditions that typically Lyapunov theory it puts on some of these. So these are more from the mathematical perspective, but many of the examples we don't need to really worry about these conditions. Okay, most of the application examples in the actual control. So there are some kind of academic examples one can give which need, like, these to be satisfied and things like that. But from an application perspective, we need not bother too much about these conditions. But we'll see this for the sake of completeness. So v is decrescent function if there exists a constant r greater than 0 and function beta of class K such that v is lesser than beta. Okay, so you remember, like, the alpha of class K function alpha was bounding this v from below, and now this is bound from above. Okay, so v is always less than this beta. It's guaranteed for any time t greater than 0. So in time the function cannot go to infinity. So that is what is condition, that it is bounded from above also by class K function. So I think it is, we have a pictorial thing. No, I think there is not that. So that is a condition, like, put for v for bounding from above also now by function of say function beta of class K. Okay, so there is a bound coming from above also. That is what is a decrescent function. Then v is radially unbounded if it is bounded from below by function alpha, and for some continuous function alpha with the additional property that alpha r tends to infinity as r tends to infinity. Okay, so now this function alpha actually tends to infinity. It is not a function which is, so if you see this function here, alpha of class k is actually going to infinity as x tends to infinity. Okay, so it is not getting saturated here somewhere. Okay, so it has to go to infinity as t tends to infinity, and it has again these bounds from the top and bottom. Okay, so this is an additional condition, this is additional property. So this alpha with additional property, but this radially unbounded condition will have this decrescency also or not, I'm not very sure about. Okay, so we'll check that. But radially unbounded function will have definitely this property. Okay, it needs to be decrescent, probably not. Okay, so the function is decrescent with bound from above. Okay, and radially unbounded if this bound from below goes to infinity as t tends to infinity, and negative definite function if it is if minus v is an positive definite function, or negative LPDF if the positive like minus v is LPDF. Okay, so these are the kind of conditions that we have more definitions. Okay, so I think these are the main kind of fundamental definitions here, and then we start using the other concept of quadratic functions. So this quadratic function, you may be, some of you may be aware about this concept, and we have partly seen it when we did the proof that okay, your kinetic energy was considered as a quadratic function, right, in terms of the velocities or the generalized coordinate velocities. Okay, so so this concept we'll see, and probably we'll stop for this mathematical preliminaries part here, and then next part we'll look at the proofs. So not proofs, like the theorems of Lyapunov and its application. Okay, so these quadratic functions typically will have this kind of a quadratic form. Okay, so you are familiar with this form where you have a n vector state, like say vector belonging to Rn space, and you are developing this form for all these n components coming up in this form. Okay, if this is a quadratic terms only, here we don't have cubic and other kind of terms, linear terms also are not there, only all the terms are quadratic in nature. So x1 x2 you can have multiplications of whatever components, but no degree no more than 2. Okay, then this form can be expressed as a x transpose ax, and where a is this matrix of the coefficients here. Okay, so you see this cross coupling terms a12 a12, they are kind of going to be same here. Okay, I can split these two a12 into one part which will go up here and other part which will come up here. Okay, so this is a kind of a quadratic form. Okay, of so for a matrix, or given a matrix, I can write a quadratic form in this kind of a fashion. Okay, so either way. And for such a form to be positive definite, or those kind of properties it can hold, there are certain conditions that mathematically have been derived. Okay, so so one can talk about the positive definiteness of such a form based on there are many ways one can see. One of the ways is like look at like minimum value of the quadratic function and see that value, if it is greater than 0, then the form is having this property of PDF or LPDF or things like that we can talk about. Okay, so for that there are, by using that such kind of a concepts of mathematical optimization or things like that, people have come up with this some kind of a tangible conditions, okay, based on these theorems. Okay, so they have proposed these theorems to give some kind of a tangible conditions for this form of quadratic nature. Now, why we are bothered about this quadratic form? Because we will use this kind of a form many places for proposing the v's that we talked about in the definition. Okay, so and then use them for some kind of a Lyapunov theorem applications. Okay, um, so these successive minors, if you take determinants of successive minors, so this is the first minor of matrix A, then there is a second minor of matrix A, and like that you can develop successive minors of this matrix A and get their determinants, and if their determinants are positive, then you say this quadratic form is positive definite. This quadratic form, yeah, is a positive definite function. Yeah. Okay, so it has continuity. We see that continuity property is existing. When it is the state is 0, you'll have this form is equal to 0, that is also existing. So only thing that we need is the positiveness or alpha function kind of a property that will come if the minimum of this function is guaranteed to be having a value greater than 0, then minima with respect to x state, of course, then this form will be positive definite. So using that condition, one can get these other more tangible properties. We will not get into the proofs of these things in too much detail right now. Okay. So you need to see all the successive minors of A to be positive to get the positive definiteness property. Then this is other kind of a theorem which says that quadratic functions are positive definite functions if the eigenvalues of A are all positive. Okay, so these are all eigenvalues of A you can find out, and if they are positive, then this quadratic form has a positive value. Okay. So we'll now see this thing in the next part of the course. Okay, so derivative along the trajectories is another concept that we develop, and that's where our function will come into picture, and then we'll see what is Lyapunov theorem for stability and things like that. Okay, so we'll stop at this point here.